So let's see, I am primarily an algorithms and sort of applied math type person. I'm not so much a computational technologist. But what I'm going to try to do here is share with you some of the problems we face and how our need for speed comes into play. Okay, and hopefully these things will be things that you would find very interesting, and you'll see them as very important challenges. But let me mention that I have had a need for speed for a very long time. When I first started working on digital television, to encode 1 second of HD content took us 24 hours. Okay? So, as you can guess, that really limited our ability to do research, because every time we came up with some changes, we'd have to run it overnight, then come back, have breakfast, get a coffee, so forth, come back, and hopefully the simulation finished, we could see the results. Times have, with Moore's Law, we've improved quite a bit since that time, but there's still much more improvements that we can, that'd be very valuable for us. Okay, let me start out by saying just a couple of words about what my work is within HP, since that may also be of interest to people here. So I'm part of HP Labs, and HP Labs is HP's central research organization. We complement the R&D from our business units, and we typically aim at research problems that are from 3 to 10 years out. Some of this is fundamental science. For example, you may have heard of the memory resistor, which was identified at HP Labs recently. So we've done a lot of really good work in nanoelectronics, molecular electronics, things like that, and other things which are much more advanced development related. We also help with the strategy creation for HP. For example, what technology direction should HP be moving in for the future, as well as, of course, tech transfer. And we have a very active collaboration with universities. There are about 7 HP Lab locations throughout the world. You can see them here. I'm based in Palo Alto, California. And we have about 600 researchers throughout the world. And this is the final slide about HP Labs that I'm going to show, but I thought it may be of interest. Our research is kind of oriented along 8 themes. You may know of HP as a printing company, and part of our research is on digital commercial print, where the idea there is that you can adapt and personalize every printed page and do this at mass scale. There's also work in content transformation, for example, flexible displays, so you can wrap up the display and put it in your pocket and take it with you. Immersive interaction, which is some of the work I'll talk about today. Information management. Analytics, which is operations research type problems. Because HP is a huge company, doing operations research really, really well is very important for us. Cloud computing. Intelligent infrastructure, such as network infrastructure, servers, data centers, and so forth. And I'll talk a little bit about this, as well as sustainability. And sustainability is at the center here because it ties in with many different, many of the other themes. Okay, so that's just a very quick overview about HP Labs. Now the topics I'll talk to you about in the remainder of this talk, some of them are things that I worked on, and some of them are things which members of my lab worked on, Multimedia Communication Lab in Palo Alto. And the last part is done by my colleagues at HP Labs Bristol, the Pervasive Computing Lab. Okay, some keys which in the computing world you're familiar with these different attributes as being important for success, and you will see these sort of attributes in my talk. But let me share a few more words about them. Since I work a lot on multimedia communication, and especially interactive communication, real-time processing is very important for me. But what I mean by real-time processing, because there are many different definitions, what I mean is, 30 millisecond slack one way or the other is okay, but you don't want to go beyond that, because that's more than 1 frame interval for video, and once you get to that point, it gets really bad. So that's the type of real-time constraints that I'm talking about. Now this is an attribute that has many, many dimensions. For multimedia communication, you want very high quality for the video, for the audio, and I can't emphasize that enough. You'll see examples of this later, but oftentimes people cut corners here, and this has very nasty effects when you cut corners. Another thing that's very important is the ability to adapt. So as we're doing processing, we adapt to the characteristics of the signal, we adapt to the context. And that's something that comes into play, because when you build computational algorithms, for some architectures, it's very easy to adapt. and in others it's not. We have a lot of control logic in most of our work, and we do a lot of adaptation, and that adaptation helps to significantly improve the performance. And finally, scaling. And scaling is very important in the work we do. And for the first half of my talk, you'll get an idea about what type of scaling I'm talking about. Okay, so here's sort of the outline of what I'm planning to talk about. First, I'm going to talk about some things that we're doing on the infrastructure side. How do we design infrastructure for streaming media delivery to large numbers of clients? As you can guess, scaling is very important there. Then I'll also talk a little bit about data networking and switches and routers and what we need to do there to enable improved computation in the future. This is something I just recently added to my talk because I thought that even though this isn't directly related to multimedia communication, it is relevant, I believe, to the Need for Speed seminar series, and I thought you'd find this quite interesting. Then I'll talk about how we can do multimedia communication, as I say, both at work and at home. And I'm contrasting this versus the infrastructure case where all the computations are hidden there, somewhere in a back room or in the data center. So in this case here, I'll talk about HP's Halo high-quality video conferencing system and what makes it work. What are some of the technical problems we had to overcome and why these problems were complex. I'll also talk a little bit about some of our work developing future multimedia communication systems for the desktop and notebooks. And since mobile clients are also an important example, I don't do any work on that myself, but I'm going to show you a quick example about what some of my colleagues in HP Labs Bristol have done. And that's an activity called Mediascapes. And I'll end with this sort of vision video. It's a little bit more marketing than the rest of my talk, but I think you may enjoy it, and it's kind of a vision of where mobile clients may go in the future. And if you can help build mobile clients that could do that, that'd be really great. Okay, so first of all, let's look at the infrastructure. What happened was in around 2000 or 2001, we started looking at overlay networks. And this was actually motivated by some problems that Docomo had. Many of you may have heard of Docomo. Basically, they're the mobile carrier in Japan. They're the AT&T of Japan. And back then, what they had is they were the first people that brought out the equivalent of web browsing on a cell phone. Okay? No images, just text, compact HTML. But when it first came out, it was a really big hit, very, very valuable. And what happened then was once they brought it out, the number of users had this exponential curve, the revenue had this exponential curve, the load on the servers also had an exponential curve, and the servers went like this. Okay? So they found out that they had problems operating at scale, even for delivering compact web pages to people's cell phones. And they wanted to go to multimedia. So then they came to us and said, okay, how should we design our infrastructure to support multimedia delivery to large numbers of mobile clients? Okay. So then we worked and helped them design a multimedia optimized overlay network. Sometimes these are called content delivery networks. Sometimes these are called content distribution networks. But these mean essentially the same thing. And basically what happens is we place servers at different strategic locations in the network, and these servers do caching for media, as well as streaming, relaying, other types of media processing, such as transcoding, and so forth. Many of you may have heard of companies like Akamai, and there was Inktomi a number of years back at Berkeley, well, by Berkeley founders. So they are also content delivery networks. What's interesting was that content delivery networks were very, very successful for delivering web pages, but they started having problems when you started delivering media, because for small media, it didn't take too much storage space. But as soon as you start talking about DVDs and so forth, the cost of the storage space here was actually pretty significant, and the cost of the bandwidth was also pretty significant. And then people started looking at P2P networks. So there's certain people looked at P2P networks because they wanted to share music without paying very much. And then there are other people who are looking at P2P networks because they were broadcasters, and these broadcasters, these regular big companies, did not want to pay the cost of a CDN because CDNs were very expensive. as an example, to deliver a DVD costs something like on the order, in some cases, of about $1. And if the delivery cost of the DVD was $1, you can see that they couldn't charge very much for actually delivering that. So that was one of the reasons people went away from overlay networks. But it's an interesting question now as storage becomes more and more plentiful, as computation becomes more and more plentiful, as our bandwidth becomes more and more plentiful. What will the preferred architecture for large-scale media delivery be in the future? Okay. This, I think, is an open question. This deserves more attention than I think it's getting. I don't know the answer for this, but I would like to know the answer. So if you come up with a really great PhD in this topic, I would love to read it. Perhaps hire you too. And by the way, throughout this talk, I'm going to try to identify different questions like this that I believe are pretty important, or different areas like this, directions for improvements. One of the things we did, well, so with our work there, we designed these overlay networks, and each one of these servers here basically is a server that streams content over a telco network, let's say a 3G or 3.5G network to a video phone. So HP actually sells a lot of this. This is a very big business for us. And one of the interesting things that comes into play here is that these systems they're measured in terms of how many simultaneous streams you can send out. Okay? So it doesn't matter what the CPU is or the memory. That doesn't matter at all. What matters is how many simultaneous streams can each one of these, can your system distribute. So the more high-quality simultaneous video sessions you can send out, the better. So this is also another area that I believe will be very important in the future, because as more and more of the cable companies, as well as the other broadcasters, want to deliver content and want to deliver personalized content to the various people, this becomes more and more important. How many high-quality simultaneous video sessions can you deliver? So HP, as well as many other companies, are trying to optimize this. And by high quality here, I mean standard definition television or HD television or higher quality. Okay. Another key functionality that happens in the infrastructure is something we call transcoding. And the basic situation is the following. You may have a sender who may want to talk to one or two receivers over here. The sender encodes the content with high resolution, packetizes it, sends it over the network. This nice laptop, which is connected via a nice wired network, he has the bandwidth to receive this high quality video. He can also has the CPU capacity to decode it, and he also has a really nice large display to display it. So he can actually receive, decode, and display everything that is sent. On the other hand, you have this person who has maybe an iPhone or an iPAC that connected with a low bitrate wireless network. So because they're connected with his low bitrate wireless network, they can't receive this high bitrate stream. Furthermore, even if they received it, they don't have the CPU power to actually decode it. And even if they decode it, they don't have the screen size to display that really nice large HD video. So what we do here is we transcode the content. By that I mean we receive the stream of incoming packets, and in real time we transcode to give us a new set of packets which we can send to this client. It can receive it, decode it, and display it. So for instance, in this case, we reduce the bit rate of the content, maybe reduce the frame rate, and reduce the spatial resolution so it can fit within the screen. Okay. Turns out this sort of functionality is very important. Some of the places this is used today is, for example, for fixed to mobile convergence. For example, we have a particular customer in Europe which originally motivated us to work on this problem, and they have a lot of people who are on a fixed network, that is a wired network in their home. So it's a wired IP network, packet-based, and they also have people who have cell phones. And those people are on a 3G network, which is circuit switched. So they have people on circuit switched who want to talk with people on packet switched. Very different bit rates, very different control protocols, different codecs. So basically what we need to do in here is go from packet switch to circuit switch. Yeah, from packet switch to circuit switch. We need to change the codecs, reduce the bit rate, and do everything in real time so that these two people can interact. Okay? So that's an example, and its use for fixed to mobile convergence. And as we go into the future, we will have an even larger range of possible networks as well as devices. These kinds of transcoding functionalities, we believe, will become even more important. Now, this is very computationally intensive. You can cut a lot of corners, but then if you cut corners, you'll see a lot of artifacts. So it's hard to do it really well. And when you want to do it well, you usually have to adapt quite a bit to the encoded video here. So everything is, there's a lot of control logic there that adapts what you're doing in real time based on the received bit stream. So that's a hard problem. And what we would like to do is to see how many high-quality simultaneous transcoding sessions can we support, let's say, per CPU over there, or per GPU, or per Larrabee, and so forth. Okay. This is another interesting problem, and this came up from one of our customers in Singapore. Has anybody been to Singapore from here? Yeah, it's a fascinating country. Great food. It's a lot of fun going there. It's kind of small, Singapore, right? So I would not have expected that they would have coverage issues in Singapore. But it turns out they have coverage issues. And what happens is that sometimes you may be connected via, let's say, for example, a Wi-Fi connection and receive a video at very high quality. But as you leave that Wi-Fi hotspot, you may have a 3.5G connection, HSPA. But as you move further, you may lose this connection. You may be on a 3G network, which supports a lower data rate. And perhaps if you move further, you may even lose that and be on an even slower network, such as Edge. Okay? So what's interesting is that even in countries like Singapore, you can have coverage issues. And especially places like the US, which are much bigger, there are many more coverage issues that can arise. And one of the things they really wanted is the ability to, in real time, transcode the content to fit it through whatever the available bandwidth is for the end user, no matter what the access network they're on. Okay? Now, there are a lot of interesting things you can do here because, for example, with this 3.5G network, this is a data network, and you can decide how much you want to share that bandwidth among all the different users. And because of that, you have some really interesting resource allocation problems that come up here. For example,
John, I want to ask a question about, instead of having a dynamic transcoding mechanism, about encoding the multiple formats statically and just selecting based on what the end configuration is.
You can do that if it's pre-stored content, but if it's a live conversation, then it's harder. And if it's pre-stored content, you're hoping that you choose these levels for the bit rates appropriately. And if let's say you code the video for 1 megabit per second, but let's say you only have, let's say you code for 1 megabit or for 500 kilobits. And let's say you only have 800 kilobits available. That means you're going to have to operate this guy at the 500 kilobit level, which is actually a big hit in performance. So if we actually do transcoding, you can actually get much better performance. So sometimes what you're saying is exactly right when you have pre-stored content. But if you have either, if we can't do the pre-stored content, if we have real-time communication, but we can't tell this guy what bit rate to hit, then this is really useful. And also if you have pre-stored content, but the granularity of the bit rates is too coarse, once again.
Yeah, I actually have a question. A lot of people in these Asian countries are watching TV on their telephone. And so I'm currently wondering, particularly from the multi-core point of view, if I'm currently TV station broadcasting to very different customers, can you actually in parallel do the transcoding to serve customers that are on a 3G or
Yes.
on a 3.5?
Yes.
So that's really where the parallelism would come
Yes.
question. And you still need real-time decoding, transcoding.
Yes. Yes. And what you can do is when you do these parallel encoding, as you may have already assumed, you can exploit the fact that you're doing these in parallel to actually gain a lot of computational benefits from going across them. Yes, yes. By the way, thank you for also asking questions. Questions are wonderful, so the more questions you ask, the better. It makes it more fun for you and also more fun for me. So please feel free to ask any questions. Okay. I was saying a minute ago about how there's some very interesting resource allocation problems here. What happens here is that with a 3.5G network, you have a certain amount of bandwidth, and you can share it however way you wish. Okay? Let's say, for example, that you're maximally using this bandwidth to serve 20 people. Okay? I'm saying you maximally use it because if you have 20 people, you want to use that bandwidth as much as possible to make their lives as good as possible. So let's say you maximally use it. Well, what happens is that, let's say a 21st person comes online and wants to communicate from the same cell. Normally you'd be in trouble because normally, in order to, either you could not allow him access, sort of a mission control sort of issue there, or you'd have to kick somebody else off in order to give him access. But if you have real-time transcode in here, what you can do is you can take those 20 people and maybe like dial down each of their bit rates by about 5% or so, and then allow the new person to come online and serve them also. So there are a lot of additional functionalities like that that you can do now because you can attack this resource allocation problem with much more flexibility than we could before. So this adaptive transcoding is very useful. So the standard ones for cell phones today throughout the world is H.263, and the default one is H.264. The optional one is H.264. Everybody's going to H.264 in the future.
You mentioned before that the static transporting is very important for the dynamic fluctuation in the network bandwidth. So I'm wondering the recent work on the fine granular scalability of the SBC kind of work in this area.
So SBC may help. The original fine granular scalability within MPEG-4, that did not provide as good compression efficiency. So that was a big problem that hurt it. So if you compare FGS versus conventional MPEG-4 coded with transcoding, the conventional MPEG-4 with transcoding would often work better. But it's more complex. It requires computation. But this is a computational seminar here, so I think you guys would hopefully like that. Did I answer your question? Okay. Let me also talk a little bit about what's happening in the network, because network infrastructure is also going to change in the future, and there are a lot of computational problems here too. The basic problem today is that from an end-to-end point of view, we have little control of the network QoS, security, mobility, manageability, and so forth. Okay? In particular, today's networks are quite complex. We often have a lot of patches which are applied on top of each other, things like NATs and proxies and so forth. Our network's also opaque. We have limited visibility in terms of what happens when a problem occurs, and especially for multimedia, you want to have very real-time visibility in terms of what's happening so you can adapt and solve the problem. Okay? We don't want to learn at the end of the day that a switch or a router had a problem. We want to know right away so we can fix it, or we can adapt the network, adapt the paths being used in order to continue to have high-quality multimedia communication. Today's network is also inflexible in the sense that it's hard for us to add new innovations to the network. And basically, we have one type of network, generally a best effort network, which doesn't provide support for other applications. So if you want something like, if you want to treat video packets differently from web traffic packets, we can't do that today. We have very limited ability in today's networks to support those sort of things. So the question comes up, how can we build a more flexible, extensible, and reliable network in the future? And this leads to an interesting question of, can we design flexible, programmable networks? And by that I mean the switch is programmable, and you also can program across your network fabric of multiple switches or multiple routers. Okay? This will allow us to add innovations to the network much quicker than the past. We can also dynamically reprogram the network to add new capabilities without bringing the network down. While the network is still operational, we can reprogram it and add stuff. Or at least that's the goal. We can leverage in-network processing and storage, as well as provide better diagnostic capability and visibility in terms of what's happening in the network and management afterward of the network itself. This can help us do a number of things, such as improved energy efficiency. Turns out that in data centers, after CPUs and storage, after air conditioning and CPUs, the networking is the next biggest energy hog. So if we can adapt the network to reduce the energy usage, that can lead to noticeable improvements in reduction of power required by data centers. So just like you may be familiar that if you have n servers, you can do job allocation in an appropriate way to minimize the CPU usage and therefore minimize the energy that's used by all these servers. The same thing you can do with the networking fabric, where you can adapt which switches you use. You can send the data over different paths and adapt which switches you use in order to minimize the energy usage. And of course, in-network media processing, such as transcoding. Some of the challenges here include how can we design a programming model that can go across the entire fabric. And we also want end-to-end per-flow handling and control. It's easy to do per-flow processing at a particular switch, but to do that over a large network in a coordinated way is much harder. And actually, here comes the biggest question. How can we design these switches and these routers so that they are programmable while still processing at their line rates? If you have a 10 gig switch, you still want that 10 gig switch to operate at 10 gig. You don't want it to slow down and be operating at 5 gig or 1 gig because you have some programming, some operations which are performed on each packet.
I'm curious, how do you envision this programmability with respect to the application programmers, right? I mean, currently we are so divided, right? I mean, the video application programmers program sort of at the overlay level, and then you have the system network administrators, they program their own layer, and there is just such a barrier. And what I actually would love to do is how I, as a distributed application designer, can actually have an entry to the network and say, configure it because these requirements currently are such and such, right? The application quality parameters. So how do you envision it that this kind of barriers we overcome?
Yes. So I would love to see what you describe in having that interaction occur. One thing is that because of security reasons, probably the system administrators are still going to be the ones who have access to the programmability over there. So they'll be, in the end, the people who will decide how are we going to program our switches and routers, because we don't want that to go down. It's like if UIUC's network went down, everybody would be quite unhappy here, right? So because of that, there'll be only a limited number of people who have access to that. But I think if we come up with multimedia networking approaches within the network fabric that work and are proved to be safe, we can then convince the system admins to use it. Yes.
Just to follow up on that question, actually, this is a very interesting technical problem. But could there be like policy issues that might stop this from ever being implemented? Like I imagine if you want to give preference to video packets, then there will be, a similar outcry like net neutrality type of things. People will say, why network, why video packets, why not audio packets, why not data packets, why not control packets? So do you envision this ever being really implemented?
So I think there are two questions there. One is, are policies which treat certain groups of packets, or maybe packets from certain individuals, preferably versus others? And I agree there are lots of different policy issues there that will come up, and issues of fairness and so forth. So there are definitely a lot of issues there. There's also one of the key things here is that we have a programmable network which you can use to allow which can allow people to have better visibility into the network, to see what's happening, if there are problems, if they are denial of service attacks, if there are other virus sort of attacks, and helping to stop that. So there are many uses of programmable network which actually don't require any policy things, and which there are many people who would love to have this working today if it actually worked and if it worked at line rates. Did I answer your? Any other questions about this topic?
This network you're talking about is controlled by one company, right? This is a service that one
Ah.
company is providing to.
Yes. So it's easier if it's owned by it's controlled by a single company. You also have federated cases, and there it's more complicated. But many of the interesting situations are when you go across networks which are owned by different companies or different
So
ISPs.
this is intended purely to coexist with the existing internet.
Yes. Yes. Any other questions in regard to this? Great. So as a quick summary of what we've talked about today, in the infrastructure side, I described a little bit about how computing, storage, and bandwidth today are still pretty expensive and limited, and that has led to certain design choices when we've done our systems. Tomorrow, these constraints will change. We can each make our own set of predictions as to which one will go furthest, but they will change, and they will then have significant implications in terms of how we can design our systems. For example, I think that the preferred architectures for media distribution, as well as for data networking, will probably change quite a bit in the future. And this is something which I think is worth additional research and investigation. For servers, as I mentioned, we really care about very large-scale processing of media streams on each server, as well as many, many simultaneous transcoding sessions occurring on the server. And those are very computationally intensive tasks. And for switches and routers, this is an area where we believe that there's be significant interest in making this fabric much more flexible, programmable, while at the same time not sacrificing the line rate. That is, a 10 gig switch, you still want to operate at 10 gig.
For the field transcoding and the line rate, is there any consideration for latency?
Yes.
So, it seems like you can operate at 10 gigs, but you're introducing 400 milliseconds of delay as you inspect the packet.
Yes.
You're going to annoy gamers.
Yes. Now what happens is 400 milliseconds of delay at 10 gig means you have a pretty large buffer there. So that means it will probably be too expensive to sell it to begin with too. So as you said, there are lots of issues, and latency is critically important. So at the beginning when I mentioned those key attributes, and one of them was high quality, latency is a key aspect of the high quality there. Yes. Any other questions? Great. Okay, let me talk a little bit now about some of the multimedia communication work, research we're doing for the work in the home. So one of the systems for multimedia communication that HP has recently introduced is something we call Halo, which is a very high quality video conferencing system. Has anybody here used Halo before? Okay. So
We'd love to have a Halo system here.
I thought you were going to bring one with you.
that would be nice. They're pretty big. So one of the problems whenever you talk about video conferencing is that everybody has used it before, and it was, I think most people would probably say it's pretty crummy, right? What you've used before. So it's hard for me to explain how good this is without you actually using it. So if anybody's out in California, let me know. I'll be happy to show you.
There's one in Chicago also.
There's one in Chicago, yes. There are about 150 or so throughout the world there. So we have quite a few, but unfortunately we don't have one here.
How much is it?
Oh, it's pretty expensive. Yeah, I don't know the actual cost, but I'll describe what it has, and then you'll see why it's so expensive. It's like $250,000 for the room, and then it's the networking cost on top of that. Okay, so what is it? Basically, what we did is we have a dedicated room which we use which we explicitly designed for the video conferencing. By the way, this effort was done initially in collaboration with DreamWorks. You may know of DreamWorks. They make Shrek and a large number of other of the computer-generated movies. And they have artists which are in the Bay Area as well as in the Los Angeles area. And what happens is these artists, they want to be able to interact every day as they try to brainstorm about what the script is, how the various characters should be drawn, and so forth. And what happens is they try to use conventional video conferencing techniques to do this daily collaboration. And it was unsuccessful for them. It didn't work because it was too awkward, too fatiguing. So what they were doing is they were flying back and forth between San Francisco and Los Angeles. Luckily, it's not that long a flight, but still, that's very expensive, time-consuming, and a big carbon footprint, right? So what they wanted is a system, a much more higher quality system for video conferencing. And they came to talk with us to see if we can develop it together. And that's what was the motivation for this project. So this was motivated by one of our customers. So what we have here is we have a dedicated room that's specifically designed for this. What happens is that there's very nice meeting geometry. So people are on a table which you're on this table, which is like a semisphere, and same thing with people on the other end. So it gives you almost the impression that you're all around a circular table. The people you're talking to is life-size, which adds to the feeling of being together, because when we see each other, we're all life-size, right? We're not like a little postage stamp or something that fits on my laptop screen. Very good lighting. As long as they sit down anywhere over here, they're nicely illuminated. Like I probably look pretty good, depending on if I'm hit by the projector. Okay, but everybody, as soon as they sit here, they look very good because the lighting is designed to make them look good. Similarly, they're also nicely framed. So as soon as you sit down, you're acquired by, the place you sit is designed so that you're nicely placed within this frame. It's not like you see half somebody's head and not the other half. See, we're used to seeing people with their entire faces because of movies and so forth. We're not used to this situation where your people's heads cut off. So it's important to do that right too. And of course, low acoustical noise. So this part of the goal of this room is to minimize the noise from air conditioning, from fans, and from other people who may be talking in neighboring rooms, because all of that is interference. In addition, it has a dedicated network which provides guarantees in terms of available bandwidth, low delay, and low loss. And because of this, we're able to have people throughout the world being able to interact with low latency. So, for example, from Palo Alto to Singapore and London, three-way conference, same time with low latency. But we're only able to do that because it's a dedicated network.
So, I mean, is the speed of light an issue?
Yes.
When you
Yes.
when you're talking about circling the world at something time?
Yes, speed of light is unfortunately too slow for the Earth. Yes. It's surprising.
So I see that the camera is put above the
Mm.
monitor. So how can you get eye-to-eye?
Yes. So one of the big problems in open research problems is the eye gaze problem. When you look at a display, the best place to actually have a camera, the ideal place, is in the middle of the display. Or actually, if you have two people here, you'd like to have the camera right here when you're looking at that person, right here when you're looking at the other person. Otherwise, you have this eye gaze problem where I'm actually looking at you, but from your point of view, it looks like I'm looking below you or above you, and so forth, depending on what the camera is. So this is one of the open problems that we're still trying to solve.
So could you explain a little bit more about how you mean by dedicated network?
So I'll talk a little bit. Oh, let me give you a quick answer now. We basically have leased lines to every customer that purchases a Halo room, and we connect them all up throughout the world so that we can guarantee bandwidth between any two of these customer nodes anywhere in the world.
So you rent a dedicated wavelength channel?
It depends on the scenario, but we basically rent sufficient bandwidth between these nodes from whatever the carrier is in that local area. So from the US, a certain set of carriers, from Japan, a different one, Singapore, a different one. As you can guess, operationally, this gets to be very complicated. But that's what we have to do in order to deal with this issue that the speed of light is kind of limited, and if you do things badly, and if you don't route the packets correctly, you have too much delay, even just from going around the world, let alone from all the encode and decode and display delay and so forth.
So under the situation here, do you do any encoding?
Oh, yes. So depending on the version, it's either MPEG-2 broadcast quality or H.264. Yes.
So will there be research funding opportunities from HPN?
I think there will be a lot of funding sources if we can.
Thank you.
So is the system support multiple point conference? Or
Yes. multiple point. And maybe I'll go on a little further because I may answer some of the other questions that you may have. Of course, it's high image and audio quality. Obviously, that's very important. And the key thing is that it works. And the only way you can tell it works is by actually sitting through a half-day or full-day video conference with somebody in Singapore, and then you realize that, hey, this actually works and it's far superior to anything else. You still have a time difference problem, but you don't have any of the other problems.
That's where the speed of light comes in.
Okay, here are just some other views. We've spent a lot of time also making the interfaces very simple and intuitive. In regard to your question, if you can, is this 2-point or multi-point? Here's an example where we can have people in San Francisco, connecting to another room in San Francisco, Barcelona, Spain, and Corvallis. So you can have a 4-way with 16 people. And you can also share, for example, share laptop information, or have an object in front of you that we have a high-def camera that focuses in on it and can use it to share with others. Now what happens, though, is when you use this system, one of the things you notice is that even though it works quite well, it still seems like you're looking through a number of windows to see the other people. And normally you don't look through a window, right? When you see me, you see the background. There is no window. So one of the things we're looking at is, can we make the entire wall actually the equivalent of a display? Because if we can do that, this can give us much more freedom in terms of what we display. And also we can sort of augment reality by placing various synthetic content there, like documents and so forth, and that can help us with the collaboration. So if we can have this large wall as a display, we have a lot of area we can use to do interesting things. Along these lines, one of the things that have been examined is how we can use, for example, multiple cameras to help acquire a better version of the scene. Everything's processed here in software over the network, and then multiple projectors on the other end. And that's what we use to show you the prior, to make the prior wall basically a display. Okay, here's another technical problem that is you may find of interest. Often we compress natural video. By natural video, I mean video captured with a normal camera, okay, and that corresponds to some scene in the real world. Well, you also want to share desktops and stuff, and this may include natural video, text, graphics, 1-pixel wide lines. This compound video, which is both natural and synthetic content, it has actually very different characteristics. And if you want to compress it, you want to really account for the source and treat it differently than the natural video. Here's just a simple example of what you can do. Here's a document which is coded using regular JPEG, and this is its reconstructed version. And this is the error between the reconstructed version and the original. And as you can see, there's pretty sizable error there. And here's an example of one of our compression schemes, which identifies that some parts of this is natural video and some other parts is synthetic. And here's its compressed version, and here's the error. So one thing you notice is the error here is much less than the error here. Another thing is that we can achieve about 3 times the compression ratio by accounting for the fact that some parts of this is a compound document with synthetic and natural stuff. So you get much better compression and much less error.
Want to focus on spatial video or for any kind of video? Because this video has a lot of text, but that is kind of spatial video.
It's designed to work, well, the algorithms are designed to work on generic compound video, which consists of natural and synthetic. And then we basically segment it into different parts based on whichever codec works the best for that and run it. But the key thing is to realize the source can consist of these 2 very different sources, natural content and synthetic content. Natural content is often very noisy. Synthetic content is very clean. It's nicely approximated by polynomials. Okay, so you can treat it very, very differently.
So can you run in real time?
I'm sorry?
Can you run in real time?
Oh yeah. So for example, if I look back here, this collaboration screen, which you share content from, for example, the laptops, that's all compressed using our compound video coder. Yes. Okay, audio. Audio is incredibly important, as you can guess, for communication and collaboration. Okay. Now, what's also, what may be a little surprising is that spatial audio turns out to be very important. And maybe I can hint at that by just reminding you about how surround sound is very useful for listening to movies, and it adds a lot to the experience. Well, spatial audio, which is similar to surround sound, where you basically capture the sound field of the people you communicate in and try to render it on the other side, that's also very, very useful. For example, some of the simplest things that come to mind in this case is that if there are multiple people at the other end, by having spatial audio, you can hear from what direction the sound is coming from, and then know is it this person or this person that's talking. And what happens is that that's very important, because if all this information is captured by a single microphone and replayed to the other side, it gets confusing for the listener. And there's a lot of fatigue that occurs, and this is one of the reasons people get tired and annoyed with video conferencing, because they spend a lot of extra mental energy trying to, this is all done subconsciously, trying to identify who's talking when and to follow the conversations. So spatial audio turns out to be very important. Let me talk a little bit about some of the problems that occur. One of the big problems is echo control. And let me just remind you what echo is. Let's say we have two people in two different rooms that are trying to talk. If the person in room B talks, he's picked up by the microphone, goes over the network, played out by the speaker. This person hears it. It also bounces around in this room, picked up by that microphone, and comes back. And he hears himself talking once again, and this is the echo. Okay? That can be very bad. And that can be very bad, especially if the end user is a space far enough apart so the echo is sufficiently delayed relative to the person's original speech. Okay? So that can be very bad. Most of you have probably have bumped into echo problems before. Many of the phone conferencing systems that you use may often operate in a half-duplex manner in order to try to eliminate the echo. By half-duplex, what I mean is they only allow audio to go this way or this way at any point in time in order to prevent the echo. You have echo when you allow both people to talk at the same time. Okay? So many of the simpler schemes are basically half-duplex, and many cell phones also are half-duplex. By the way, full duplex, allowing both people to talk at the same time, is very important. As an example, when you're probably brainstorming with your colleagues about a technical problem, you're probably saying something, then your colleague says something, and you go back and forth, right? And you're almost interrupting each other and so forth, and that actually adds to the brainstorming. The only way you can do that is if audio can go both ways at the same time and without any echo. Okay. And there's some nice signal processing problems here. Now, from a computational point of view, this turns out to be quite difficult. The reason is we want very high quality audio, so we actually sample at 48 kilohertz. CDs are 44.1 kilohertz. This is higher sampling rate than CDs, and it's 16-bit per sample. Okay. This is an example of the impulse response of an echo in a halo room. And as you can see, it goes out to 300 milliseconds and on, and it's still pretty big. Basically, because of our high sampling rate and because of this very long length in the impulse response, we basically have to track about 20,000 parameters in our adaptive filter and optimize these parameters to eliminate that echo. So an adaptive filter with 20,000 parameters, which are updated every, I forget, it's like 50 milliseconds and stuff, is a pretty complicated problem. Okay? I'm sorry? That's a lot of parameters, and that's what we find we need to do in order to keep the audio with the full spectrum. To sample at 48 kilohertz, so we have an audio bandwidth of about 24 kilohertz. What happens is having this broadband audio for the communication, even though our speech generally is much less bandwidth than that, turns out to be helpful, and it gives people it helps to add to the naturalness of the situation. Because if we're talking like this, somehow or other, we're filling up that full spectrum that our ears can hear. And if we cut that off in the video conferencing, it has detrimental effects. Okay, so single channel echo control is difficult, but let's go to the real problem. The real problem is multi-channel echo control, which is what we need for spatial audio. Okay, so by multi-channel, for spatial audio, in essence, what we want to do is we want to have multiple microphones in a room to pick out the audio sound field capture it, send it over the network, and render it on the other side. Okay? Let's say we have 3 microphones in each room, and therefore 3 speakers. 3 microphones here, 3 speakers in the other room. The other room also has 3 microphones, which sends content to the 3 speakers in my room. Okay? So let's see what happens. So in the other room, let's say the audio, we want to look at what happens for the audio which is captured by the leftmost microphone. It'll come to this room. It'll be played out by the leftmost speaker. It'll bounce around the room, and it'll be picked up by the 3 microphones in this room. So one audio signal will lead to 3 echoes because it'll be picked up by these 3 different microphones here. Similarly, for the center audio signal, it'll also bounce around the room and be picked up by 3 microphones. And the same thing for the right one. So if you have 3 audio signals, you'll actually have 3 times 3, or 9 echoes, which you have to estimate and eliminate. And just to make things fun, we actually only have 3 observables, which is the 3 microphones, and we have 3 known pieces of information, the 3 inputs, and we have 9 unknowns, and 9 times 20,000 parameters to estimate. So it gets pretty complicated. And in the future, we want to go to even larger number of microphones in order to better capture the sound field. For example, if you want to capture the sound field in this room here, which is pretty broad, we probably want to have a large number of microphones. We don't know how many. There's still very important research questions there. MIT has this example with an array of 1,000 microphones. But it's nicely structured on a rectangle, and that may not be the best situation for here. But there are a lot of open questions. How many microphones? How should they be arranged? And so forth. But here's the key point. If there are n microphones, we have n square echo paths. So the complexity for the adaptive filters and so forth grows as n square, and things get really complicated very quickly.
But at some point, would increasing the number of microphones make life easier because you can use spatial information to just filter out audio from a speaker?
You can use beamforming and a variety of techniques, and all of those are part of the package, but it still turns out it's a quite difficult problem. Yes. So this 3-channel echo control problem, this was an open problem in the research community, and we believe we're the first who are actually able to solve it and get a working system. Yeah. Many of you may know Ron Schaefer. He helped write a text on digital signal processing as well as one digital speech processing. He was part of the team that helped develop this solution for us. He's in my lab at HP Labs.
Can you hack this down a little bit so that it's a little easier to figure it out? Because you're the one who generated this.
Yeah. Also, what's played here is known. So these signals are known, but the impulse responses for the room are what are unknown and time variant. And for example, whenever I move around, it completely changes the impulse responses for the room. So these are some very interesting and complex problems.
Even if you could sense them all over the space across the room, the production would require placement of speakers in similar position.
Yes, and it's interesting to see, because there are certain tricks we can do. This is an area of active research, and we would like it if we can find ways so we don't have to place speakers all over the room. And in some special cases, the tricks we can do where we don't need to do that. But this is an active area of research, and any new innovation along those lines would be wonderful. We don't know how to do that. Okay, let's see. So I described what we're doing with the Halo video conferencing. What we also want to do is extend this so that people can use it basically anywhere. So you can have something on your desk which you can have an experience similar in quality. By similar in quality, I mean you can have a natural and effective video conferencing experience with somebody else as if they're in the same location as you are. That's what we'd like to be able to do if possible. So then we want to, for example, design our PCs and design our notebooks so that we can try to achieve this. Now, this turns out to be a very difficult problem. And let me just briefly summarize why it's difficult. And we could do this by contrast in the case of Halo and why Halo works. So for Halo, as you saw, we had a custom room. It's basically like a movie studio. Great lighting, great acoustics, nice placement of the people, great cameras, great displays, you name it. Here we want, in our case, to be able to work in a generic office or cube environment, or maybe in somebody's home. The lighting is often very bad there. There's often a lot of noise. You often have shared office spaces where the people nearby you, and as well as fans and so forth. All of those has to be eliminated. So there's a lot of visual clutter and noise in the environment that can be very distracting. We somehow need to eliminate that. Similarly, Halo uses a dedicated managed network in order to provide basically the guaranteed QoS that's necessary to have these high-quality communications throughout the world. On the other hand, we want to work on an enterprise or a home network or a wireless network, and you know what these are like. Sometimes our web pages get delays here. So we have limited bandwidth, we have loss, we have delay, and everything is time variant. So we try to estimate what the available bandwidth is, and then depending on congestion network, it can change very quickly. So these are very complicated problems. I want to give you an example of one of the prototypes we have working here. So what we want to do is we want to get very high quality video. So for us that means HD video, for example 720p. And we want to send it over the average network that you may have. So this is one typical scenario. You may be at home with a notebook computer. You may have a regular, let's say, Comcast cable modem. This is a high bit rate going down, but up it's only, it's much smaller, maybe 1.5 megabits per second or so. Then you have to go through the internet, then through, well, if you're a company, the corporate firewall, and then the enterprise network. So there is a sequence of challenges here. Okay, two things to note. One, I'm saying we want to do this with high quality, which means we want to send a lot of bits through this channel. I don't mean 128 kilobits, I mean much, much more, because we want a much high quality. And two, this is a lot of challenges that you have to go through. What I'll do next is show you just one example of something we have working in software, H.264 real-time encoding, 720p, basically on a laptop. And that's what I'm showing you. This is operating in this exact scenario. And that's what I'll be showing you here with this big video. And what I'm showing you here is what you can do with a Skype video today, just as a comparison. So I think what you'll see when you look at the two of them is that there's much more spatial resolution on this side than there is here. For example, you can read the text here much easier than you can here. The motion is also much better motion rendition here. The frame rate is much higher, and you don't have this abrupt starts and stops. So this is an example of what we can do with putting all our tricks together, running in real time, H.264 encoding on one of our computers. Okay, here are some of the other research problems that we're trying to focus on. One of the key ones is better understanding the user experience. What are the essential elements that make this sort of collaboration successful, and what are the things that make them not successful? As engineers, we may pick the wrong problems to tackle. Right? So we want to figure out what are the problems that really matter so we can focus attention on those. For video and audio, the compression, the delivery of the time-variant network is critical. That's one of my favorite problems. For video processing, we often want to do, for example, some sort of computer vision-based pseudo 3D rendering to deal with the eye gaze problem. You often want to, for example, do video segmentation to extract the people, the participants, and replace the background by some more normal background or some background that is not distracting. Because if you're at your work or at your home, you may have something happen in the background that you don't want other people to see. And even if it isn't for that case, if there's a complex background there, it often turns out to be fatiguing to the end users. So you want to have a very simple background there that does not distract attention. And for audio processing, as I mentioned, spatial audio is very important, and therefore we want multi-channel capture, processing, and rendering everything in real time.
So I have a question. What is the order of priority if you have a limit of time and resources and you want to develop one of them? So what is the priority?
What is a priority? Well, we're working on all of them because they're all important. It depends on the application scenario. For instance, if you're trying to work from home, then you have a very bad network typically, and this problem turns out to be the most important. On the other hand, if you don't have this problem, but you're trying to interact with people, sometimes the eye gaze problem is the most important. So this is a long discussion, and perhaps I can talk with you more afterward. Okay. I probably should be finishing in a minute or two, right?
Yeah.
Okay, so let me show this slide, and then I'll just show that other brief video which I had. These are some important technology trends which I think will come into play, and hopefully you're familiar with many, if not all of these. But if not, I want to briefly describe them. There's a lot of effort throughout the world on improving sensors. A lot of effort, and this will actually help quite a bit. Part of the reason video conferencing is so bad today is because the cameras are so bad and the microphones are so bad. In the future, we're going to have many cameras, high quality, 1080p, 60 frames per second, as well as high dynamic range. Cameras today are 8-bit, but in the future we'll have more 10 and 12-bit ones. And this will also help in the cases where we have low light and help in terms of the noise issues there. These cameras have to be synchronized too. 3D cameras are very important. By 3D cameras, I mean a camera which captures a regular 2D image, which is composed of red, green, and blue pixels, as well as an estimate of the depth of each one of those pixels from the camera. Okay? For audio, the acquisition and rendering is going to be continue to be very important, and we're going to have a larger number of both microphones and speakers in the future. And there are a lot of interesting questions as to how this should be designed. How many microphones? Where should they be placed? Should they be, if you're all around a table, should they be placed in a circle around the table? There are many different many different possibilities here, and we're still trying to figure out what are the right ones. Speech recognition, of course. I'm sure you're familiar with this. Visual gesture recognition is also something that's very important. When we talk, when we collaborate, part of what we're doing is talking, part of it's the motions, and part of it's the hand gestures. Okay? And you can use hand gestures to accomplish different things. Many of you are familiar with touch-based computing like iPhone and so forth. Well, visual gestures is just an extension of that. And what we'd like to do is to be able to accurately estimate visual gestures, track them, and use them to help with the human-computer interfaces. Okay, so maybe what I'll do now is I'll just show you this last video I have at the end. This is kind of a vision video describing what one may be able to do in the future with mobile clients. And as you'll see, this is something that requires a lot of computer vision, computer graphics, and computation in order to make possible. So here it goes. And So that's an example of something we'd like to do in the future. That's an extension of some of the work of our HP Labs Bristol team on pervasive media and a project we call Mediascapes. And as you can tell, there's a lot of computer vision, computer graphics, augmented reality, communication involved to get that to work, and that would be a nice thing to make possible. Thank you.
Thank you, John. So we have time for a few questions.
So I have a question as far as the audio capture question is very difficult to resolve as the echo problem. So, but there's an easy solution. If you have any participants in the room, they have their dedicated headphones and the microphones, and there will be no echo problem. So what's the motivation that you don't want to import this kind of system and have easier emulation of the environment and rendering into each participant's headphones instead of having speakers all around the room?
Yes, you're right. And some people are happy to wear headphones and mics like that, and in that case, it works great. But for many people, that's not a natural way to interact, and they prefer not to have headphones and a mic, and therefore we're trying to solve it for the more general case. But you're right. In places where things are very bad, we can resort to this scenario, and it can help resolve a lot of these problems. Mm-hmm.
The remote we were asked on the echo cancellation issue, could you or do you emit a sound that people can't hear that helps solve the echo cancel problem?
You can.
Would you mind repeating the question? Actually, we should repeat the question.
Sure. I think what you were suggesting is add in some sort of training signal into what's played out by the microphone that's inaudible to to humans, but that could be used to help in the echo control. Yeah. So it's a great idea. It's used a lot in digital communication and other places. To my knowledge, in the audio field, that hasn't been very successful. But I don't work in that area, so I would recommend to talk with some others who are experts in that area. We talked about it before, and it wasn't a good solution for us. Yeah. Oh, by the way, one other thing I'll mention about your question, your suggestion for this. What happens is that when you wear a headset, it actually is often more fatiguing than if you don't wear anything. So we're trying to identify and eliminate all of these things that either consciously or subconsciously make this interaction fatiguing. And thereby allow people to have a more natural, seamless interaction with others.
So when we do these phone conferences, one of the problems is when people speak farther away from the microphone or closer to the microphone, there's a very big dynamic range of these things.
Yes.
And do you guys just use enough microphones to cover it, or you actually do some kind of compensation of dynamic range to make it better?
So we do not compensate, and part of the reason for that is we want to make it as if you're in the same room. And if the same room and you're far back and you're talking facing the corner, people won't hear it. So we want you to act naturally, which means you sit by the table, and so we don't do any of those other equalization or so forth.
But you probably add more microphones.
We do have more microphones, so we can capture people everywhere on the table. We have 3 microphones, and we have 3 independent audio signals. Yes.
I was curious about the spatial audio. For example, if we are here in this room, if somebody asks question far away, that particular sound is softer or not as loud as, for example, somebody stands next to you. In this distributed environment, do you reconstruct this kind of relative distances around the table? If somebody is very far from me versus if somebody is sitting next to me?
So in Halo, we reconstruct exactly what we hear, which means if somebody is soft and far away, we reconstruct that. In a more general situation, we're not sure what's the right thing to do. Because if you have distributed cameras and distributed microphones, there are ways to use that to try to better capture people who may be soft-spoken or may have a cold or whatever, and make it easier for other people to hear them. Now, whether or not that's actually a good thing to do is an interesting question, and we're not sure. Was there?
Yeah, for this N-square echo problem, so you mentioned need for speed. So I guess you will need a parallel kind of solution, but it's kind of DSP multi-core solution, because this is not general purpose, right? So do you find any useful chips out there that can serve?
In fact, John, let me ask a more Deming's question, but more general. What's the computational solution that you have right now in Halo? What does that look like?
So for basically all of the things I showed you there, if they're not custom ASICs, they're all running on IA32 standard commodity CPUs, high-end ones, but with C code and assembly code. So no DSPs, no FPGAs or anything else.
Okay, so you find that's sufficient. For example, how about GPUs? Is there a need for that?
So we are looking at GPUs for different things, and there are many open questions as to what is the right solution. A GPU, Larrabee from Intel. There are many open questions there, at least to us, as to what's the right platform to do in the future. By the way, some of the other issues that come into play are cost, reliability, power, heat, noise. For example, noise is a surprisingly big issue, because we want these, for example, for Halo Room, it has to be very quiet. You don't want fans. But many of these solutions, they often have big, powerful fans as part of the heat sinks to draw away the heat. And we can't actually have that then in the same room as the participants, because the fan noise is distracting. So it's the many different issues that come in play in terms of choosing
Take one
architecture.
final question here.
Okay. Maybe I could ask a question about the need for ergonomics. It seems like a lot of these motivations are based on human factors. How does human factors fit into the engineering of this room at HP?
So what happens is we have a number of people in HP Labs who are either engineers who are interested in the human factor side, or psychologists, anthropologists, so forth. You know, they publish in places like HCI and so forth, and that helps quite a bit in terms of understanding what are the essential elements of the experience that we want to accurately represent. Because you're right, as engineers, we'll probably tackle the wrong problem. I'll tackle something that has a lot of nice math, and I'll miss something that really matters to you.
Thank you again, John. It was a very, very
Thank
nice
you.
evening.